Everyone, I'm Liao, a PhD student in Dr. Piezo1's lab at Duke University. I'm glad to present our recent work on ultrasound neuromodulation. In this study, we investigated the optimal ultrasound parameters, especially the pulse length, for Piezo1 mechanosensitive ion channel activation and intracellular calcium response. Despite the unique advantages and growing interest of using ultrasound in neuromodulation, the specific mechanism of ultrasound neuromodulation is largely unknown, and the optimal ultrasound exposure condition for eliciting neural response with minimal adverse effects have yet been clearly identified. To address these issues, we developed a novel and miniature ultrasound platform to deliver ultrasound stimulation and acoustic streaming-induced shear stresses to single HEC293 T cells transfected with Piezo1, while monitoring simultaneously the cell displacement, membrane paration, and calcium signaling. We swept the pulse length to determine the safe and effective range of ultrasound exposure for Piezo1 activation and intracellular calcium response. We performed numerical simulation and pressure measurement to characterize the performance of our transducer. We found that acoustic streaming-induced shear stress is the dominant factor for eliciting the calcium response in this study. We observed inhomogeneous distribution of the von Mises stress inside the cell at both the leading and trailing edge along the shear flow direction. We varied pulse length but keep the same total acoustic energy delivered to the cells. We found calcium response in the Piezo1 transfected cells are highly sensitive to pulse length, with the strongest response observed between 10 and 100 milliseconds as shown in figure B to D. Outside this range and either shorter or longer pulse lengths, the calcium response became much weaker. Quantitatively, we found the intracellular calcium wave speed, response duration, response rate, and intracellular uptake all peak at 20 milliseconds and show a biophasic dependence on pulse length. Also, we observed with increasing pulse length, adherent cells are more likely to be detached and paraded. The activation of Piezo1 is known to be directly linked with the cell membrane deformation produced under tension. We found the temporal cell displacement showed a creep recovery response characteristic of biologic tissue and cells subjected to impulses of mechanical stress. Much pronounced displacement was observed at pulse lengths greater than 10 milliseconds. We calculated the time integral of cell displacement and found it reveals a biophasic dependence on pulse length, with a distinct peak at 20 milliseconds, which resembles the profiles of the response rate of Piezo1 transfected cells at different pulse lengths. We have also adapted and modified a four-state model describing Piezo1 kinetics in electrophysiologic measurement. Especially, the model can be used to reveal the intricate dynamic interaction between the open, closed, and inactivation 1 and 2 states of the Piezo1 channel under dynamic loading. We plotted the current integral on the cell membrane under tension during insonification calculated by the modified four-state model. We found the simulation results demonstrated a similar biophasic dependence on pulse length, with a peak achieved at pulse length equal to 20 milliseconds, as observed from the experiment. In summary, we have shown that Piezo1 activation depends critically on pulse length, with a distinct peak produced at 20 milliseconds under the constant acoustic energy. Also, the cell mechanical properties impose a filtering effect of ultrasound stimulus, and the intrinsic Piezo1 inactivation contributes to the filtering effect. The implication for future work is to further develop optimal ultrasound protocol for specific application and target. That's all for my presentation. Thank you for watching.